All right, so we're going to take a look and do a little bit more work with section 10.1. It's kind of the day 2 notes. So I passed this out in class yesterday, and we're just going to kind of talk about one quick thing, and then we'll kind of get back to yesterday's example, and then actually create a confidence interval out, take what we did yesterday with respect to the confidence interval and actually make a hypothesis test out of it. A lot of similar things there. So again, so for tomorrow, what I'd like for you just to concentrate on is obviously getting this, getting this done. Smart board's not working. There we go. Okay, so again, get this Mythbusters simulation piece done for tomorrow. That was the extension part. So either if you know a little about coding, Python or Java or something like that, go ahead and work on it that way. Otherwise, you can use StatKey. I'm happy to help if I can a little bit. Just send me an email or something. Let me know. So if you go to the notes that I passed out yesterday, there's this quick blurb that actually came out in the AP listserv that I belong to, and again, it's just sort of a clearinghouse for people to ask questions, and some smart folks check in on that every once in a while and write some really nice replies to some common questions. And so the question here that actually prompted this response is this guy here. What is when checking the independence condition for intervals and hypothesis tests, are there specific times when one of the following typical arguments would be considered far better than the other? And so this is a response by Dave Bach, and Dave Bach is pretty well known in the AP Stats community. He's a professor, has written several textbooks, and usually writes some pretty thoughtful responses here. So I'm going to let you go ahead and read that. Please do that on your own. But the basic idea here is that this mathematical independence is one thing. That's usually what we think of with the 10% condition. Sometimes that fits. Preserving independence of observation. That's pretty much just making sure that the data is coming from a good source, and I'll let you read a little bit more about that. This is what we called this the within groups independence, and then the groups themselves. If we're doing we're comparing two groups. This is what we're doing now. This is kind of the between groups independence. Okay, and kind of what he says here at the end is that all these, you kind of got to figure out which one fits in what situation and apply them appropriately. So I'll let you read through that. You can pause, of course, to do that if you want to, but I'm going to go ahead and go on to the next question. And so this is what we did yesterday, just to kind of review that idea a little bit. So we had this preschool example. We kind of set up everything for a confidence interval. We talked about, again, no past tense when we're defining those parameters. We did a confidence level of 0.95. The test that we're actually doing is a 2-sample z proportion for the confidence interval. And so that's actually the test that we did yesterday. We checked for, kind of checking our conditions here, at least 10 successes and at least 10 failures in each group. And so, that kind of gives us this idea that since that's the case, then everything is sort of approximately normal there, at least the sampling distribution. And then we looked at independence. We talked about how this was not really sampling, so we didn't really have to check that 10% condition. But it was really important for us to sort of establish this independence between the groups. That's, again, the randomization provides that creates two groups that should be roughly independent from each other. And then within the groups that, the subjects aren't really interacting with each other a whole lot. They're not affecting one another's responses or need for those social services later as adults. Kind of got to the calculations. Did a little bit better with this in 4th period than 8th period. But this was the idea. This confidence interval sort of comes from this basic formula that we've been using here. It's an estimate plus or minus the critical value times the standard deviation. Of course, the estimated difference is based here. Critical value comes from the z-score, 1.96. And then we sort of calculate the standard deviation. It's similar to what we did yesterday. Sorry, exactly what we did yesterday, but it's similar to what we've done in previous units, with sort of combining that standard deviation piece. That gave us a confidence interval of here. Again, we had, the folks that were in the preschool group had a 61% chance of needing social services. In the non-preschool group, it was 80%. So what that led to was, this kind of confidence interval. Actually, we calculated it, and I just want to kind of take a look at this other part here at the bottom. So an interpretation of that. So basically the idea here is, again, it's confidence interval. So we could be 95% confident the percent of needing social services is somewhere between 3.3 and 34.7% lower among those who have preschool compared to those who don't. Okay, so we're pretty confident here that there is some sort of a difference here, and we've estimated that it would be somewhere between 3.3 and 3.7% lower if children were allowed to go to preschool, or if those if those services were actually provided at an early age, as opposed to kind of needing to provide them when those young people turn into adults. Okay, so that was kind of the gist of. Oopsies. That was kind of the gist of that particular problem here. Oh, speaking of problems. Huh. Well, let's try this one. Well, as you can see, I'm continuing to have problems here with my smartboard, so I apologize for this. Something went wrong there. There we go. Okay, so 10-1, day 2. Again, we're going to take a look at the same situation, except we're going to create a hypothesis test today. So yesterday, we really looked at answering this question. What is an estimated? What is an estimate for the difference between the two populations? We sort of figured that out towards the end of class yesterday. I just kind of reviewed that a little bit today. Today, we want to look at, does that study actually provide significant evidence that this preschool is actually creating good, right? It's actually, definitively, with significant statistical significance, it's actually made a difference, and that's what we're looking at today. So estimating what that difference, make a decision, is it in fact a difference? Okay, so a lot of space here to work on this, so whoopsies. All right, so we're going to do this 4-step process. We don't have to do all of it because a lot of it, gosh, give me 1 second here. I'm so sorry about this. I got to calibrate this board. So again, the idea here is that a lot of what we did yesterday will sort of spill over into today. We're still going to do this 4-step process. So we're going to state, we already defined parameters yesterday. So we'll just sort of save that here. Usually we would do that, but we already have that done. And so those are the same parameters as what we're looking at today. Again, we're P1 and P2. We don't want any hats in those because we're, again, trying to say that this is going to, these results would apply to similar kids in similar situations. So our null hypothesis here is simply going to be this, that P1 is equal to P2. Okay, the intervention with preschool early on made no difference whatsoever. The proportion of kids who needed social services as adults is exactly the same as that for kids who did not attend preschool. And then also we can have this, our alternate hypothesis would be that P1 is less than P2. Remember that P1, those actually were the kids who had preschool. So we're anticipating, hoping to find evidence for a lesser need for social services as adults. You can also write this, by the way, like this, kind of depending on how you want to do it. You can write P1 minus P2 is equal to 0, or P1 minus P2 is equal to 0. Sorry, not equal. Greater or less than 0. Those are the same things. So whichever you want to do there is cool. Part 2, which is the plan step. We already checked the conditions yesterday, so we're not going to belabor the point there. So, but we are going to actually, perform this test here. We are going to perform a 2-sample z-test for proportions. A 2-sample z-test for proportions, and we're going to use a significance level of 0.05. kind of make some note here. The conditions were checked yesterday. Okay, so we don't need to continue with that. Step 3 here is the do step. This is our calculation piece. So, you know, our test statistic here, and we'll kind of go to this formula sheet that we've been working off of. Our test statistic is always according to this basic formula here. So it's always a statistic, whatever that happens to be, minus the parameter divided by a standard deviation of that statistic. And so let's bring that back out to this page here. And so our test statistic statistic minus the parameter divided by the standard deviation. Now, specific to this one, again, you would not have to write any of this, and I would encourage you not to write this because, again, using those wrong variables, misusing that notation as automatic points off in the AP test. I'm going to write it out here just so, for your notes you can have it. The z-score in this case, because we are working off a normal curve, we sort of verified that yesterday. Our z, and again, the statistic here is actually what is that true, or sorry, not the true difference, but what is the difference that we actually found in the two test groups that we had. So here we actually would have a p hat 1 minus p hat 2. That entire thing is the statistic because we're trying to find a difference there. Is there actually a difference between those two? Now the parameter in this case is just going to be 0 because the null hypothesis tells us that there is no difference between the two. So that's the parameter. Now our standard deviation is a little bit more complicated here, and so this is a point where we need to have a conversation. So remember, let's see. So remember that our null hypothesis up here, let's see if I can switch to a different color. Yeah, our null hypothesis here is how we want to sort of proceed with the whole test. We want to sort of assume that that's true and continue with that line of logic throughout the whole thing. Since it's a hypothesis test, again, we're assuming that that null hypothesis is true. And if that is actually true, that these two are in fact true, then, I guess, we go back to the standard deviation calculation, and this is kind of the way that we did it yesterday. We're actually using p hat values for these things. We're using p hat 1 and p hat 2. And there is a little bit of error, in that calculation. More to the point of sampling, like we're expecting some variability there. We don't expect p hat to be exactly what it is in the larger population. So there's a little bit of error in that calculation. And the idea is that we always want to try to create a situation where there is as little error as possible. It's a really good thing for us, small error. And so the idea is that we can actually, if we use this equation just as it is, then we're going to actually be getting a little bit more error than what we need to. The idea is to kind of decrease the error of that measurement. And so I guess we'll go back to this. And what we can actually say is if this is true, if P1 is equal to P2, well, we ought to just be able to combine those two samples into like a really large sample. Because as our sample size increases, the accuracy of that measurement is going to get better and better and better. It should be, in theory, closer to what the true population value is if we have a larger sample. So that, and combined with the fact that we are, assuming that this is true, our assumption is that those two population values are exactly the same. Let's just put the two proportions that we have into one big super sample. And again, this is something that we could not do yesterday because in the confidence interval, we did not have the assumption of the equality of those two proportions. We were just trying to find an estimate for the difference. Here we have that we're saying that they're equal, so let's just sort of roll with that. Okay, so the idea here then is really, and then maybe we'll come over here somewhere, right? I don't know how this is going to all come together here. But actually maybe a separate page would be better for this idea. Okay, so what we want here is we want to create this new statistic called p hat c. This is called a pooled or a combined proportion. A pooled or a combined proportion. C means combined. Okay, so in a broader sense, we call it pooling whenever we sort of put those two or pool those two samples into a larger sample. So the idea here is that really what we do to find that p hat sub c, that combined proportion, is we take the total number of successes and divide it by the total sample size, I guess, what I would put there. Total sample size, or group size in this case. Okay. Now, as kind of using some of the things that we did yesterday, would be the number of successes all put together divided by the total numbers here. This one in particular, and we're not adding fractions, right? So I probably shouldn't have maybe had that like that. We're not actually adding the fractions, we're putting them together. But this first piece here, the top and the bottom of this first part, would be the number of successes over the total number. And the second part here, kind of the same thing, the total number of successes in that second group divided by the total sample size or the total group size. Okay, now for us, what that means is that remember that we had 38 successes in one group and we had 49 successes in the other. And our sample sizes were 62 and 61, so we had 87 total successes out of our large pooled or combined proportion or group size of 123, and that equals about 0.707. And so what we're going to do is we're going to use that as, since it's a larger sample, we expect it to be more accurate than either of the two individual ones because of larger sample size. We're going to use that in our formula. Okay, so let's go back to this other page. We'll kind of piece that in here. So this again is going to be our p hat combined times 1 minus p hat combined. Now the samples, if I just kind of work with the formula here, it's still going to be, still going to have a sample size here. This is going to be the same numerator, and I'm going to have the second sample size in that second denominator. Okay, so that part stays true. And again, really strongly suggest that you never ever write these formulas out, because if you forget the hats or you make a misrepresentation with some of the notation there, you can get points deducted, which would be bad. So I'm going to do that. So more than likely, here's the part kind of where you're going to want to start this. It would be totally fine just to say, well, z is going to be equal to this. Our actual proportion, our statistic in this case, one of our proportions was 0.613, the other was 0.803. And then we subtract off that parameter again. Down here, we're just going to write the formula itself. P hat combined, this is 0.707 times 1 minus 0.707 divided by 61. And again, 0.707 times 1 minus 0.707, all over 62 in this case. So we have, again, our big standard deviation formula here. We're just making a slight adjustment because of that hypothesis. So we can calculate that, kind of punch that in, and what we end up with is this. It's about a 19% difference between the proportions, and the standard deviation as calculated here is 0.0819. And so what we end up with is a z-score that is negative 2.319 standard deviations below the mean. Okay, now again, sort of conceptually here, that's what that means, and you should include this somewhere. Our null hypothesis says that there's no difference whatsoever. The standard deviation of this is going to be 0.0819. We had a value out here that on this scale here was actually a difference of negative 0.190. And so what we have figured out essentially is this, in terms of z-scores, this is negative 2.319. deviations away from what we would expect with that null hypothesis. Okay, and since we already have that normal model, then we can just create our p-value here. So our p-value is based off of our normal CDF. Punch that into your calculator, but essentially a normal CDF, put some small number in there, that's the lower bound. This negative 2.319 is the upper. Leave 0 and 1 the same. And what we end up with here is a p-value that is equal to about 0.0102. Again, which of course is pretty small in this case, less than our significance level. So we kind of go back to that idea. This is all the calculation part, and so we finish with our conclusion here. Okay, our conclusion would be something to this effect. Since our p-value is less than alpha, and again, make that specific connection there, put the numbers in there. We're going to reject the null hypothesis at the 0.05 level. And then, so that's kind of our formal conclusion. And of course, we always want to write something that's makes sense in context. What does that actually mean with respect to the problem? And so we can do that here and say what the data provide significant evidence that poor children similar to these who attend preschool, again, making sure we're not putting in past tense there. So children similar to these who attend preschool need less social services as adults. So that kind of wraps up the significance test piece of it. Again, there were some new things there with respect to, particularly with that the p-hat combined pooled proportion. That's a pretty big idea. Just real quick, I want to show you also, because this calculation is pretty complex. It's pretty easy to get, maybe put the wrong thing into your calculator. There is a way to check it, and again, I encourage you just to use the calculator to check these. You have to show the numbers put into the formula correctly, but your calculator can do all this stuff too. So if you take your calculators out, and take a look at what we're going to do there. I have to shrink this a little bit somehow. Maybe we'll just be able to see that much of it. So we go into statistics. We'll do, let's do the confidence interval. We can do a stat test too, but if we go to confidence intervals, the one that we want here is this 2 proportion Z interval, option number 6. This is what we did yesterday. So our number of successes here, really just kind of defining what those groups actually are. So we had, 38 out of 62. We had 49 out of 61. Confidence level of 0.95%. So again, just each of the groups here and the number of successes. And then what you see here as we kind of look here, we had this, this was between, about 3.3% and 34.7%. That's what we calculated yesterday. And so, that's kind of helpful there. It also gives you the difference, the actual difference between the two proportions, what the individual proportions were. You can also go back into that stats menu and run a significance test. So if you go down to the stat tests, we want a 2 proportion Z test. So that's this one. And again, we can put that same information in there, 38 and 62, 49 and 61. This is not a two-sided, but we're kind of looking for P1 is going to be less than P2. So change it to that one-sided. And we'll
get this, and notice that these numbers are roughly the same too. We have a negative 2.32, which is about what we calculated up on the board. Pretty small p-value here. Again, it gives us those proportions, what the combined combined proportion is. So that is actually in there as well. And then, of course, the p-value is what's of importance here. Also gives us the z-statistic. So everything is there. So I would encourage you to kind of use this. It's really super quick to to show that, or just to do that quick calculation to check your work. Okay. So, again, that's probably it. So Mythbusters simulation for tomorrow. It's Thursday, and I will see you then.